Here's another sample dynamics problem. This is also something that could be on a quiz. This is difficult enough for a quiz. So take your time, press pause, take your time to work through it, and then we will start and work through it together after when you press play. Now in this case, I want you to be careful. There's this angle here, so I don't want you to be thinking, oh, there's an angle, then I'm going to be splitting gravity into mg cosine theta and mg sine theta. So my normal force is equal to mg cosine theta. No, this object is not on an incline. This is just on the ground, but someone is pulling upwards on that object, and they're pulling upwards at this angle. So this is not an object on an incline. The only time you break your force of gravity mg into those components, mg cosine theta and mg sine theta, is when your object is sitting on an inclined plane. That is not the case in this problem. When I draw my free body diagram, my normal force is pointing straight up, my force of gravity is pointing straight down, friction is going to point to the left. I don't know yet whether that's kinetic friction or static friction. And then I have this tension because Alice is pulling on a rope, but she's pulling upwards at this 30-degree angle. So in order to figure out what's happening with the crate, and I'm going to need to calculate my net force, I need my net force in this y direction. And there's a component of this force in that direction. And there's a component of this force in this horizontal direction. How do I figure out my components? Well, the magnitude of this vector is 50 newtons. And it's making an angle of 30 degrees with the horizontal. So I just do my normal thing the way I break up vectors that I've normally done. There's my 30 degrees. What I'm going to do is redraw my free body diagram, except I'm going to break this vector into a vertical component equal to t sine theta and a horizontal component equal to t cosine theta. Going from this vector to these components is not new. This is what we've been doing for weeks and weeks. Okay? So don't let all the stuff with the inclined planes confuse you and make you think that you don't know how to take a vector and break it into x and y components. Okay? Now I can look at what's happening in the vertical direction. My normal force will not be equal to mg in this case because I have another force in my vertical direction. So let's figure out what my normal force is. So I'm going to look in the y direction. In the positive y direction, I have n and t times sine theta. And in the negative y direction, I have mg. My net force in the y direction is always equal to mass times acceleration in the y direction. So I set those two things equal. Or, you might be able to look at this up here and just say, I know my net force in the y direction should be 0. This object is not suddenly going to start to accelerate in this direction. So you might have just been able to look at this and set this whole term here equal to 0. Or maybe not, and we put it all together, and then you get to here, and that's when you realize the acceleration in the y direction is equal to 0. So I plugged in all my values here, and I'm solved that my normal force is equal to 122 newtons. Now, we do not know if this object will move. I need to check how big the force of static friction is going to be, and I need to see how big the maximum force of static friction is going to be, and I need to check to see if this crate will move or not. So I'm going to say, will the crate move? I'm going to compare the maximum force that static friction can possibly supply to the other force that's pulling in that horizontal direction, which is t cosine theta. So the maximum force that static friction could ever supply is equal to mu sub s times my normal, which is 36.6 newtons. T cosine theta is equal to 43.3 newtons. So what does this tell you? Static friction cannot supply enough force to keep this object stationary. So the object will move. This force is less than this force. The object will move. Friction will be kinetic friction. So now I can look in the x direction. I know the friction I'm dealing with is kinetic friction. So I'm adding up. In the positive x direction, I have t cosine theta. In the negative x direction, I have my force of friction, and now I know it's kinetic friction. My net force in the x direction is always equal to my mass times my acceleration in the x direction. And what I'm just going to take one more step to say, what is my force of kinetic friction? It's just equal to mu sub k times my normal force. I already know what my normal force is. Here I can plug in all the values, and now I can solve for a sub x.